Get started. How did you guys find the guest lecture last time? Interesting material. He was covering a method that is becoming more popular for these kinds of model inference problems. It's got a lot of use in some fields. It's beginning to become a more popular thing for biological context specifically, and something I don't usually cover, so I was hoping that would be good material for you guys to learn a bit more about kind of the cutting edge of some of these model inference things. So I guess we'll be continuing today with some of our topics in model inference. I should point out I have your homework fours and solutions. We'll append those back at the end of class. What I wanted to do today is kind of pick up from where we left off a week ago. So we have been talking about the problem of model inference, and what I hope I convinced you a week ago is that we already know a lot of techniques we can use for inferring models. So we know now that you can pose the problem of finding an optimal model as an optimization problem and use any of our general optimization techniques by converting quality of the model into an objective function. And you can also pose a model in terms of a probability function, typically a likelihood, and use the sampling techniques we've seen as a way of sampling over possible models and kept coming up with estimates, not just the best model, but also probability distributions over models consistent with the data. So what I wanted to do for most of the rest of this module of the class is go beyond those kind of generic techniques for optimization and sampling and talk about some techniques that are more specifically used for model inference. And what I want to do now is introduce a technique that's very widely used for these kinds of problems called expectation maximization. So expectation maximization is basically a kind of optimization technique, and it's an optimization specifically for optimizing models expressed in terms of probabilities, but it's a technique that's very widely used for model inference, in part because it tends to be a very easy thing to use. It tends to give you very simple ways of coding up optimizations for probability models where it would be hard to solve for them by the other kinds of techniques we've seen. So I will say that the theory of this technique is usually a lot more complicated than the practice of the technique, but I did want to go through the theory, and then we'll see some examples which will hopefully illustrate how you use it. But basically, what this is typically used for is a couple of different kinds of optimizations. And one case where we would typically use this is to find a model, and the model we'll think of as really the set of parameters that specify a model among a universe of possible models. And in the literature of this problem, this is canonically referred to as lambda. I was calling this M in some of the previous lectures, but I'll use lambda here because if you look up the references, that's what they're using, such that we maximize a probability of a vector x given this lambda, and I suppose I should say lambda is technically a vector as well. I'll usually be dropping the vector sign and just be aware of this. So x would be our observed data, what I was calling D in the previous lectures. Lambda is our model, and this would be the most common use of this kind of technique. So find the model, maximizing the probability of the data given the model. Does anyone remember what that's called?
Maximum likelihood.
Yeah, so this is a maximum likelihood model. Less commonly, you'll see this for a somewhat similar kind of problem statement, and that is find model lambda maximizing probability of lambda given x. This is usually a harder thing to pose, and usually these are more or less interchangeable modulo some scaling factors you can estimate. This is known as a maximum a posteriori probability map model. So very often this is what you really want. You'd really like the model that's maximizing the probability of the model given the data, but you usually find this, and they're just, Bayes' theorem or rules of conditional probability say that they're proportional to each other, so it usually doesn't matter which you use. And it's usually easier to phrase your problems in terms of maximum likelihood. So I'll be assuming we're doing maximum likelihood for most of this, but just be aware that that's an alternative you'll sometimes see. So any questions about that? Okay, so that's what we're going to be trying to do with this. And we've seen various examples of likelihood problems. And the idea behind how we would solve, let's say, a maximum likelihood problem is, with expectation maximization, to try to throw in some extra information that we wish we knew that would make it very easy to solve the problem. So generally, the key to expectation maximization is to propose what are called the latent variables. And latent variables are something we come up with that we don't know, but that would make the problem easy to solve if we knew it. And these we'll canonically refer to as a vector y. And in general, what we're trying to do is find the model such that it's easy to do the following two things. Find the maximum over models of the probability of x and y given the model. So find the maximum likelihood model for the joint probability of x and y, and find the probability distribution y given x and lambda. So if you can come up with a set of extra variables about your problem that you get to propose, where it's easy to maximize the likelihood if you knew the latent variables, and it's easy to find the probability distribution over latent variables given a known or assumed model and your observed data. If you can do those two things easily, then you can easily get at least an iterative optimizer for the models. And that's how this technique is going to work, by iteratively going through successive rounds of model improvement, and usually doing a very good job of converging on a good model for your data. Does that make sense to everyone? Okay, so I will say that when we get into the theory in just a couple of minutes, things will start to get more complicated, but usually you don't really need to think too much about the theory to use the method. Like I say, it's a lot easier to use than to study the theory behind it. But I want to say a little bit about the theory. And the theory is usually explained in terms of a concept called the expected log, which we'll define as Q of lambda and lambda bar, so two possible models, and it's defined as follows. So it's a sum over y of probability of y given x and lambda bar, log probability of x and y given lambda. Right, so this is it's called the expected log, because basically what you're doing is you're taking the expected value of this joint probability of x and y, or expected value of the log of that joint probability given the model. So the expected value, the likelihood of the observed and latent variables, and it's expected relative to the distribution of the latent variables. And a lot of the technique is phrased in terms of trying to optimize the model for the expected log, and basically going back and forth between trying to figure out this probability distribution and trying to optimize your model relative to that probability distribution. That's going to be the basic iteration of this. So formally stated, what the method is as follows. We will express Q of lambda and lambda bar given y, and what this usually means is finding this probability distribution over your latent variables, and then find lambda, maximizing Q of lambda lambda bar over y. And these are generally referred to as the expectation or E step, because we're trying to find the expectation of the log, or really we're typically trying to find the probability distribution, and the maximization or M step. And basically the algorithm consists of just initializing and going back and forth between E step and M step. Now I say that's formally because very often what we're doing is something somewhat simpler. So I will distinguish between the formal algorithm and what I'll call the real algorithm. And the real algorithm is usually find distribution of y given x and lambda, optimize lambda given x and distribution of y. And even that's kind of overstating the complexity of it somewhat, because as we'll see when we go through the theory, very often the algorithm will allow you to do something even easier, and that is find the expected value, let's call that E of y given x and lambda. So often you don't even need the probability distribution of y, you just need the expected value of y, and then find optimal lambda given x and the expected value of y. And when we go through the theory, we'll see the exact conditions under which you can get away with this, but very often you can pose the problem in such a way that you only need the expected value of y, which is usually a lot easier than estimating its full probability distribution. So any questions yet? Okay, well, let's go through the theory then, and I'll try to point out as we're going through the theory what this tells us about the actual use of the method in practice. And then I think the main way to learn about EM is to go through examples. So I'm hoping today we can make it through a couple of examples of EM use in practice. But basically, the idea behind EM is that we will want to take some model, which we'll call lambda I, and one round of EM, so one E step and one M step, is going to be finding a lambda I plus 1 such that we improve the likelihood of the model, or in other words, such that probability x given lambda I plus 1 is greater than or equal to, or really we'd like it to be greater than, probability of x given lambda I. So that's going to be the goal of the EM method. And what we'll do is walk through some transformations that show us how we can guarantee that by using EM. And the first thing we're going to do is use a transformation we've seen before, and that is just take the log of everything. That often makes it much easier to work with likelihood functions. So we'll take log probability of x given lambda I plus 1 is greater than log probability of x given lambda I, and that's the thing that we're going to be trying to guarantee here. And what I'll do is walk through some theory that shows us how EM will actually guarantee that that's the case. All right, so the first thing we're going to do is start with probability of x and y given lambda, which is usually the thing we're really going to be working with because we're going to throw in these extra latent variables. And then just by the laws of conditional probability, that's equal to the probability of y given x and lambda, probability of x given lambda. And if we take a transformation here, we can say that's equivalent to probability of x given lambda is equal to probability xy given lambda over probability of y given x and lambda. So far I haven't done anything particularly complicated here, and then what we'll do is just take the log of both sides. So log probability x given lambda is log probability x and y given lambda minus log probability y given x and lambda. All right, so so far all I've done is take a statement of the probability function we're working with, do some transformations, and take a log of that. The next thing we're going to do is try to get rid of the y's, in a sense, by throwing in the expectation step. So taking the expectation of both sides of this equation relative to y, which is going to give us sum over y of probability y given x and lambda I, log probability of x given lambda is equal to sum over y probability y given x and lambda I, or excuse me, probability y given x and lambda I, log probability x and y given lambda minus probability y given x and lambda I, log probability y given x and lambda I. All right, so this is, excuse me, this should be x and lambda. All right, so what we've done here so far is just take an expectation over the value of y given the current model inference. And then we can simplify a little because we can note that on the left-hand side, at least, we've got something that doesn't have a y in it. Probability of x given lambda doesn't have a y in it, so the expectation of that over the probability distribution of y is just this thing. So we can throw out the expectation on the left-hand side, and what that's going to give us is log probability of x given lambda is equal to this expectation y over y, probability y given x and lambda I, log probability of x and y given lambda minus, again, expectation over the probability of y given x and lambda I, log probability of y given x and lambda. Okay, so is everyone with me so far? Okay, I guess I'll keep going here. All right, so the next thing we're going to want to do then is take this function and subtract a version of that from itself where we're going to plug in lambda I for lambda. So just take exactly what I've written here and then subtract it from the same thing except with lambda I replacing lambda. So in other words, what we're going to end up with is log probability of x given lambda minus log probability of x given lambda I. So just subtracting the left-hand side of this from the left-hand side with lambda I plugged in is going to be equal to sum over y of probability. It will be a little easier maybe if I simplify a bit before we get there. So let me just take one basic observation here, and that is that this thing that I've got written here, some expectation over y of log probability of xy given lambda, is actually an instance of this thing I called the expected log, q of lambda given q of lambda lambda bar, where we have as our lambdas lambda I and lambda. So in other words, this thing is going to be equal to q of lambda lambda I, and then we're going to subtract from that q of lambda I lambda I. So just plugging in this thing here for different instantiations of lambda and lambda bar. And then what we're going to do is subtract out this thing, expectation over probability y given x and lambda I, log probability of y given x and lambda, minus, I'll just put this in the sum here, log probability of y given x and lambda I. So again, all I've done here is made the substitution that this thing, the right-hand side with lambda I substituted for lambda. So I know that's a lot of notation there, but I say look at the notes and you'll see that each step kind of follows from basic probability. Any questions yet at this point? Okay, so the next thing we're going to do is make an observation based on this function here. And what this thing is saying is that we're taking the sum over y, basically the expected value over this distribution y given x and lambda I, of the log probability of y given x and lambda minus log probability of y given x and lambda I. And actually we're subtracting this, so basically what we're doing is subtracting something where we're taking the expectation of the log probability of y over the log probability of y for the same lambda minus the expectation of the log probability of y over a slightly different distribution, so a different model lambda, so basically over model lambda here over model lambda I here. And the important point behind that is that this thing here, the log probability of y given x and lambda I, is the thing that maximizes log probability of y given x and lambda over all possible lambdas relative to this probability distribution, y given x and lambda I. In other words, the thing that maximizes the likelihood of the log probability over the distribution is the same thing that maximizes the likelihood of the probability over the same probability distribution, which is just using the same probability distribution. So basically what all of this is getting to is that this part of the term, expectation relative to arbitrary lambda, can't be larger than this part, expectation relative to lambda I, when we're taking an expectation relative to lambda I. So what all of that is trying to get to is that this thing is positive, this final piece of the component, this final component of the equation. And what that gives us is a very crucial piece of information. Since this thing is positive, that's telling us that log probability x given lambda minus log probability x given lambda I is greater than or equal to q of lambda I minus q of lambda I. So these are equal if, well, they're equal minus this thing. This thing has to be negative, which means the left-hand side is greater than or equal to the right-hand side. Okay, does everyone follow that? Again, I know this is a lot of notation to cover on the board in class, but it's all in the text, so you can go through, or you can go through the references that actually have the primary proofs of this thing. But basically, I'll ask you for the moment to take my word for it that some basic rules of probability and this observation that lambda I maximizes this likelihood here over all possible lambda gives us this equation here. And once we do that, what we're recognizing is that if we're able to get this probability distribution of y relative to lambda I, then we're able to establish that this has to be true. And that basically is the E step. So basically when we're doing this expectation, we're doing the E step of the algorithm. And once we've done that, then we can use the M step of the algorithm. And the M step is the thing that is going to optimize Q. That's basically what the M step is. We're trying to pick lambda to optimize the expected log relative to a y estimated from lambda I. And what that's telling us is that by definition, if we perform the M step, then it must be the case that Q of lambda I plus 1, lambda I, is greater than or equal to Q of lambda I. Or excuse me, or Q of lambda I. And because Q of lambda I plus 1 is the thing that maximizes this over any lambda in the first position, what that's basically telling us is that it has to be better than the Q we had relative to the previous lambda. And so that's going to tell us that this piece of the equation, if we plug in lambda I plus 1 here, has to be positive. It has to be the case q of lambda I plus 1 lambda I minus q of lambda I is greater than or equal to 0. And so we can throw in the next step that if we've chosen our lambda to be lambda I, or lambda I plus 1, then probability of x given lambda I plus 1, or minus log probability of x given lambda I, has to be greater than or equal to 0. Because it's greater than or equal to this minus this, and this is greater than or equal to 0. And that basically gives us the final piece of the proof that log probability of x given lambda I plus 1 is greater than or equal to the log probability of x given lambda I. So that basically is why the EM algorithm works. And it's kind of walking us through the major steps that we need to do to solve this. We're doing the E step when we take this expectation, so basically figuring out this probability distribution. And what we've shown is if we get that accurately, and we can optimize lambda I plus 1 to maximize the value of this, that's the M step. That's going to give us an improvement in the likelihood of our model. And so, are there any questions about that yet? All right, so there are a few things we can observe from that proof. One of them is that we don't actually even need to maximize lambda I plus 1 here for the proof to go through. So the proof depends on the fact that q of lambda I plus 1 lambda I, that is the expectation with respect to y sampled for lambda I plus 1, maximized over the value of probability of x and y given lambda. This has to be better than this. And what that tells us is that all we have to do is improve on lambda a little bit for the proof to go through. We don't necessarily need to find the best possible lambda. We could use a local optimizer to improve lambda. So that's sometimes referred to, we do that as weak EM. So in other words, locally optimize lambda I plus 1 given the distribution of y and given x. So if we do a local optimizer, just improve on it a bit relative to lambda I, that still works. That's in contrast to strong EM, which is, strictly speaking, finding the maximum likelihood lambda I plus 1. And we can also observe that if we are able to pose this maximization problem in such a way that the maximum likelihood estimates of lambda I plus 1 are linear in the values of y, then we can actually get away without ever doing the expectation. So in particular, if you can express maximum over y of the sum, or maximum over lambda, some probability xy given, or excuse me, some probability y given x lambda, log probability of xy given lambda. If you can express that in such a way that the maximum likelihood estimate of lambda is linear in the terms of y, then by linearity of expectation, you don't even ever need to figure out the probability distribution of y. You can just plug in the expected value of y into your formula, and it's going to give you the same answer. And again, that's something, it's not so obvious from the theory why that would be helpful, but as we'll see, very often that turns out to be the case. So just remember that for the moment. If you can express your maximization step so that the terms of lambda are linear in the variables of y, then it's enough just to find the expected value of y in the E step. Any questions about any of that? Okay, so that basically is the method then. And as I said, I think it's hard to follow from the theory, but often much easier to follow from examples. So what I want to do is jump into an example of where we could use EM to solve a biological model inference problem. And I've got a couple of examples here drawn from the literature of computational genetics, and in particular for problems related to what's called haplotype frequency estimation. So I have to explain a bit about what a haplotype is, and then we can talk about the methods we will use to try to solve these problems by EM. So haplotypes are something we typically refer to when studying genetic variations in an organism. So if we look at genetic sequences for different people, let's say, what we might find is that in a particular region of the genome, one person has a sequence that looks like this, or maybe one chromosome of one person. That's kind of important. And maybe on the other chromosome, that person has a sequence that looks like this. So it might be that some of the bases can be different between the two strands of a chromosome in a particular person. Most of them will be exactly the same in both chromosomes in every person, but some of them will differ. And maybe if we have another person, their sequence is going to look like this. So maybe another person has also a lot of the same bases, but some of the bases differ from one chromosome to another, or they might be that this person has A on both chromosomes and this person has G. But the key point here is that every so often you will have a base that varies between different copies of the chromosome in an organism. And this is commonly referred to as a single nucleotide polymorphism, or a SNP. And the haplotype frequency estimation problem comes up because very often what we want to know is how are these combinations of SNP alleles, these bases, distributed within a population. So what fraction of people have an A here and an A here, or what fraction of chromosomes, what fraction have a G and a T, or an A and a T, or a G and an A. So those combinations are referred to as the haplotypes, and what we might be interested in is finding how common they are in a population. So classically, the reason this was hard to do is that sequencing machines that we would use to study this can't tell the difference between the two strands of a chromosome. So this isn't improving. There are ways of solving that now, but classically the way this worked is you would take a person's genome, you would put it through a sequencing machine, and what would come out if, let's say you were a person who had chromosomes 1 and 2 here on the two homologous copies of some region of the genome, is that the sequencing machine would say you have an A in the first position and a C in the second position and a mixture of A and G in the third position, A, G in the fourth, G in the fifth, A in the sixth, T in the sixth, mixture of A and T in the seventh, C in the eighth, C in the ninth. And then it becomes ambiguous what the haplotypes are. We don't know from looking at a person's sequence genome in this region if they've got the AA haplotype and a GT haplotype like we have in the first person here, or if they've got an AT haplotype and a GA haplotype like we have in the second person here. Those would look exactly the same coming off of our sequencing machines. So does that make sense to everyone? All right, so what we would then want to do is be able to take the sequence from a population and resolve these ambiguities. So by taking this ambiguous data, where we don't know how the haplotypes are distributed, figure out how common each of the haplotypes are in the full population. Now, if we just had one of these ambiguous bases in a region we were looking at, there'd be no problem, because you'd know that the A allele is on one chromosome and G on the other. But as soon as you have more than one ambiguity, then it becomes unclear what version you have. So that's really where the problem gets tricky. And that makes this an inference of what we would sometimes refer to as an incomplete data problem. We've got ambiguous data, and we're trying to get at the ground truth behind that ambiguous data. And that tends to be a kind of problem where EM is very often useful. So EM very often works well when there's some hidden data we're trying to infer from an ambiguous output of that data, or an ambiguous version of that data. So to see how that works, what I'll do is simplify and formalize the problem a little bit. And I'll formalize by saying, first of all, that when we're trying to do this frequency estimation, we don't care about any of the bases that don't vary between individuals. So we'll reduce this to just looking at the bases that are variable between different people within the genome. So we've got 2 of those in this example here. And we'll go further and just say that we don't even really care that these are A's and G's and C's and T's. All we really need to know is that at each site there's a set of alleles, and then we need to know which person has which allele. So a common way to represent that would be to say that we'll just at each site call one of the alleles 0 and one of the alleles 1. So maybe we'll turn this into the sequence 0, 1, 0, 1. So we'll call A0 at the first site and G1 at the first site, and then 0, 1, 1, 0. So we'll call A0 at the second site and T1 at the second site. And that then would be the set of haplotypes in a more abstracted version. In some sense, this is what we're trying to find. We want to know at least how many of each of these there are. How many 0, 0s, how many 0, 1s, how many 1, 0s, how many 1, 1s. So does the problem statement make sense to everyone? Okay, so that's the output we're trying to look for. And what we're going to be assuming then is that we get an ambiguous set of input in which we are getting pairs of chromosomes and we're seeing the alleles kind of mixed together on each chromosome. And the way we commonly represent that is by defining what are called genotypes. And a genotype would be something that would tell us either we have a pair of 0s, or we have a pair of 1s, or we have a 0 and 1. And we can't tell the difference between 0, 1, or 1, 0 at a given site. So in other words, what we would say is, if the haplotypes at a given site are a pair of 0s, we'll call that 1 input. We'll call that a 0. If the haplotypes are a pair of 1s, we'll call that a 1. And if it's either a 0 on the first chromosome and a 1 on the second, or a 1 on the first chromosome and a 0 on the second, we'll call that 2. And so if these were 2 people, then these inputs would both look like 2, 2, 2, 2, even though they're different combinations of haplotypes. So in other words, what this is getting at is that we're assuming our input is this 0, 1, 2 alphabet of genotypes, and the output we're looking for is the 0, 1 output alphabet of haplotypes. Does this make sense to everyone? Okay, so this is something we would typically be doing at a population level. You can't necessarily resolve this for any particular person, but you can say over an entire population, what are the frequencies of these kinds of haplotypes? And to do that, what we typically assume is that we've surveyed some population and we've counted the genotypes. So let's just assume for the moment, to keep it relatively simple, that we're looking at a situation like this where there are 2 variable sites, 2 SNPs in our genome. Our input vector then, so the known variables, would be counts of how often we observe each of the genotypes. So we would have a count N00, which is how often we get the genotype of 2 zeros on the first chromosome, and 2 zeros in the first position, 2 zeros in the second position. N01 is how often we observe 2 zeros in the first position, 2 ones in the second. N02 is how often we observe 2 zeros in the first position, and a 0 and a 1 in the second position, and so forth. So N10, N11, N12, N20, N21, and 22. So we have 9 possible genotypes here. We're assuming we have counts of all of these. If we had k sites, it would be 3 to the k. Yeah?
So when we convert it to 2, 2 there, we're assuming the first 2 sequences are 2 copies of the same, from the same person?
Well, we're assuming here that the first 2 sequences are the 2 homologous chromosomes from the same person. It's the same region of genome in the 2 homologous chromosomes. Any other questions about this? Okay, so this then would be our input. And what we're trying to figure out are our frequencies. So the haplotypes don't have 2s, there's no ambiguity. There would be some frequency of a 0 on the first chromosome, on the first site, a 0 on the second site, frequency of 0 on the first site, 1 on the second site, frequency of 1 in the first site, 0 in the second, and frequency of 1 in the first and 1 in the second. So if we had k sites, we would have 2 to the k possible haplotypes and 3 to the k possible genotypes. And we're assuming we've got counts of the genotypes, and we're trying to infer frequencies of the haplotypes. So does that make sense to everyone? Okay, so if we want to solve for this problem, we want to find the maximum likelihood model given the data set, the first thing we need to do is pose this as a probability function. We need to have some way of expressing what our likelihood is given any possible model and any observed data set. And the way that would be commonly done in this field is to assume what's called Hardy-Weinberg equilibrium. And Hardy-Weinberg equilibrium means essentially that we assume that the 2 chromosomes in each individual are chosen independently of one another. So in other words, it's an assertion that the probability we see an individual with haplotype 1 on the first chromosome and haplotype 2 on the second chromosome is going to be given by the frequency of haplotype 1 times the frequency of haplotype 2, independent of one another. So that's Hardy-Weinberg equilibrium, and this assumption that what you have on one chromosome is independent of what you have on the other is not necessarily going to be exactly true, but it's close enough for a well-mixed population that we can use it to get a probability function. All right, so if we do that, then we can start talking about the probabilities of different genotypes. So, for example, we can say that there is a probability of a 2-0 genotype. And the probability of the 2-0 genotype we could get by thinking of all the possible ways we can build that from haplotypes. So a 2-0 genotype could mean we've got a 0-0 haplotype paired with a 1-0 haplotype. Then we'd have a 2 in the first position, a 0 in the second position. Or it could be produced by assuming we've got a 1-0 haplotype paired with a 0-0. So in other words, the same thing, just flipping the chromosomes. That's always going to be symmetric. And that's going to come out to 2 times the frequency of 0-0 times the frequency of 1-0. So that's telling us if we had just one observation of the 2-0 genotype, this is the probability with which that should occur, or the likelihood of that particular data point. Does that make sense to everyone? Okay, so suppose we had a 0-1 genotype. What's the likelihood of that genotype? How could we make that out of haplotypes?
0, 0, and 1, 1.
Yeah, so it has to be a 0-1 haplotype paired with another 0-1 haplotype. So what then would the likelihood of that be in terms of the model? Yeah, it's going to be the frequency of the 0-1 haplotype times the frequency of the 0-1 haplotype, or x01 squared. And once we know how to get likelihoods for particular observations, it becomes straightforward to get a likelihood function for the entire input data set, so the set of counts of all of the observations. So basically, if you've got the likelihood of one observation, then you just take the product of that over all of the observations to get the full likelihood of your data set. And what that's going to give us is the likelihood, probability of x given lambda, is going to be the product over our genotype, so every possible genotype in the set 0, 1, 2 to the power of 2 of the probability of that genotype to the power of the number of observations of that genotype. That's just taking the product over each independent observation, or in other words, what we would end up with is that we will have a component for the number of N00 zeros, or number of 00 genotypes we observe, and that's going to be the likelihood of producing a 00 genotype, which is F00 squared, raised to the power of the number of 00s we observe. So this is the portion of the likelihood that accounts for the fact that we've observed N00 genotypes of type 00. And we need to multiply that by all of the other examples. So we'll observe 01 genotypes. Each of those is a likelihood F01 squared. We've got N01 of those. We'll observe some 02 genotypes. Those have an individual likelihood F00, F02, F00, F01, times N02. We'll observe some 10s. That's the power N10. We'll observe some 11s. Probably with likelihood F11 squared to the N11, and so forth. So 2 F10, F11 to the N2, 2 F00, F10 to the N20, 2 F01, F11 to the N21, and 2 F00, F11 plus 2 F01, F10 to the N22. And this one is worth a little comment here. So if we're considering the 2-2 state, that's where we have to account for the fact that, well, basically there are 4 different ways of producing it. We can either have a 0-0 paired with a 1-1 or a 1-1 paired with a 0-0. So those are symmetric. Those are going to give us this term. Or we can have a 0-1 paired with a 1-0 or a 1-0 paired with a 0-1. That will give us this term. We raise that to the power of 2-2. Does that make sense to everyone? Okay, so that basically is our likelihood function. And what we want to do then is optimize the f values, so optimize lambda for the n values to maximize that likelihood function. So for the most part, this would be easy to do. So basically, we can pretty much figure out for these observations what haplotypes they contributed. So everywhere we see an N00 observation, we know that this is contributing 2 00 haplotypes. Everywhere we see an N12, we know this is contributing a 10 haplotype and a 11 haplotype. So almost all of the observations, we actually know exactly what haplotypes they're contributing to the population, so we can figure out how much they contribute to these Fs. And the only real problem, if we're looking at just 2 sites, is the N22 case, because that's the one where we don't know just from seeing a 2-2 which haplotypes it's adding to the population. So really, that's the thing we need to focus on. That's the ambiguity in resolving the data. And that, as I say, is a kind of problem where EM tends to be very useful. And so what we're going to try to do is come up with a way of solving this by EM. And as I mentioned, the key to EM is to come up with your latent variables. So it's to figure out something that you wish you knew about your problem that would make it easy to solve the problem of, well, I mean, basically that's probably the simplest way to put it. A piece of information you wish you knew about your problem that would make the problem easy to solve. And it's a little more complicated than that because you need to be able to estimate that piece of information. But let me pose the question that way. What piece of information do we not have here that would make it easy to solve this problem? Well, one of the reasons EM tends to be really good for these kinds of ambiguous data problems is that it's usually pretty easy to figure out what you wish you knew that would make it easy, and that is you wish you had the information that would let you resolve the ambiguities. So that's what we're going to assume for our latent variables here. The ambiguities are the genotypes, the haplotypes. So we know what genotypes we have. What we want to know is what haplotypes we're producing those. And so what we can do is just assume that we have counts of the actual pairs of haplotypes. So we're going to define our y to be how many times do we see a 0, 0 paired with a 0, 0? How many times do we see a 0, 0 paired with a 0, 1? How many times do we see a 0, 1 paired with a 1, 0? And so forth. And those will be our latent variables, because if we knew these, it would be very easy to figure out our haplotype frequencies. We just count how often each haplotype occurs. And most of these we actually do know. So most of these are very easy to figure out. So what is G0000? In terms of our input values, how would we express this? How many times do we have haplotype 00 paired with haplotype 00? Well, this uniquely produces the genotype 00, and we're assuming that's part of our input. We know how many 00 genotypes we have. So this latent variable G of 0000 is just N00. So the number of pairs of 00 haplotype with 00 haplotype is the same as the number of 00 genotypes, because that's the only way you can get a 00 genotype. Does that make sense to everyone? And some of the others we can also figure out. So G0100 is sort of ambiguous, because we don't know whether 01 is on the first chromosome or the second chromosome when we observe a 01 paired with 00. But we can pretty much just say, since it's arbitrary whether this is 0100 or 0001, we can just arbitrarily say that these are equally frequent. So half the people we observe will attribute to having 01 on the first chromosome, half on the second, and so we can say that those latent variables are both 1/2 and 02. So these are the only two ways to get a 02 genotype. We'll just attribute half of each of those to the 02 genotype. Does that make sense to everyone? Okay, so the only one then that's tricky really is trying to figure out the 0110 genotype or the 0011 genotype, or the flipped versions of those 1001 and 1100. We don't know how frequent each of these are, and we can't figure that out directly from the input because those would all be observed as 2-2 genotypes. All right, so that then is where we're going to want to come up with an EM algorithm. And what we want to be able to do then is, first of all, come up with a way of saying what would the M step be, so what would the maximum likelihood estimates of the F's be if we knew the latent variables. So in this case, if we knew all of these latent variables, we know which haplotypes are found in each of our observations, then it would be pretty easy to come up with the F variables. So the M step of our algorithm would just be estimating the F's, so those are our model. And what we can say is that the frequency of haplotype ij is just the sum over all haplotypes xy of the gij xy haplotype. And then we can add in that we would also add in the sum over g xy ij for possible xy's. So basically we're adding up all the observations that have an ij haplotype on the top and all the observations that have an ij haplotype on the bottom. And then we just need to normalize these, since this is a frequency, with the sum over xy of nxy. That gives us a population frequency. Does that make sense to everyone? Just saying, if we had this hidden information in latent variables, that's how we would estimate the haplotype frequencies, because we're assuming from the latent variables we know all the haplotypes, so we're just counting and normalizing. And the important thing here is that we can observe that this function is linear in the latent variables. So all we're doing is taking a sum over the latent variables, normalizing by our observations, which don't change, so those are our data points. And because this is linear in the latent variables, that means that we don't actually need to know the probability distribution over the latent variables, we just need their expectation. So basically, if you have a linear function f, so given linear function f, the expected value of f of a vector g is equal to f of the expected value, or excuse me, expected value of f given g is equal to f of the expected value of g. In other words, you can take the expected value of the y's, plug that into the formula, and you'll get the same answer because expectation is linear. So does that make sense to everyone? Okay, so just remember that for the moment, and what that's going to let us get away with is a simpler e-step than we would otherwise need to worry about, because all we need to do then is figure out the expected values of our latent variables given our current value of the model and our observed data points. So in other words, we need to be able to figure out for any genotype, let's say 0, 0, 1, 1, what is the expected value of that latent variable, the count of 0, 0, 1, 1s, assuming that we know the model parameters Fij for all of our haplotypes, and assuming that we have our input data, the x's. Right, so the way we would figure this out is, well, for most of them, as I said, we can just figure it out directly, but for these 4 ambiguous ones, the way we would figure this out is to say that some fraction of our observations will be attributable to this pair of genotypes. So the only way we can have one of those is if we've observed a 2-2, and then we need to figure out, in expectation, what fraction of our 2-2 genotypes are attributable to this pair of haplotypes. And the way we would do that is to say that there is some probability of producing this pair of haplotypes, that according to our model is F00, F11, and then we need to divide that by the probability of all the possible ways of producing that pair of haplotypes, which is going to be F00, F11, plus F11, F00, plus F01, F10, plus F10, F01. And what that's telling us is what fraction of the 2-2 observations should be attributable to a 0-0-1-1 haplotype pair. Does that make sense to everyone? Okay, so that then is going to be the same as G of 1, 1, 0, 0. We're assuming those are equal. And then the alternative value we would get is G of 0, 1, 1, 0. We could say that whatever haplotypes aren't, whatever N22 observations aren't attributable to this pair or this pair must be attributable halfway to this pair and half to the inverse of that, so G of 1, 0, 0, 1. But let's walk through how we would figure that out to actually pose the formula. So what would be the formula to figure out the expected value of G 0, 1, 1, 0? How could we pose that? Well, the only way we can have a 0, 1, 1, 0 is if one of our 2-2 genotypes was attributable to this pair of haplotypes. So just as here, we want to figure out what fraction of the 2-2s are attributable to this haplotype pair. So how would we pose that? What would the numerator be?
F10 and F0.
Yeah, so we have F10, F01, that's the probability of choosing those two haplotypes, and then the denominator would be the same thing we have here. Effectively 2 F00, F11, plus 2 F00, F1, F1, 0. So that, and these two formulas plus this formula are pretty much the entire EM algorithm. The only other thing you always need to do with EM is you need to throw in some kind of initialization. And the initialization is usually something kind of ad hoc. You try to come up with some way to get the method started. In this case, what we can do is throw in kind of a simple thing and say that since the only ambiguities are the 2-2 cases, so these things here, we'll just assume that the 2-2s are equally attributable to each of these 4 possibilities. So each of these will start out as 1/4 of n2-2. And then that would give us a way of estimating our latent variables. And once we've got the latent variables, we're just going back and forth between the M step and the E step. So the E step gives us the expected latent variables. So we initialize, we run an M step to get the model, we run an E step to get the latent variables, run an M step to refine the model, E step to refine the latent variables, and so forth. And if we actually work through this, we could see how, or we could try this on some real data and see how this would behave. I give an example in the notes. I don't think it's worth necessarily going through all of this in great detail, but basically that's going to give us the algorithm for our problem. Do whatever initialization you want, and it can matter how you initialize. Sometimes these are local optimizers, so you do want a decent initialization, then just go back and forth, estimate the model given the latent variables, estimate the latent variables given the model, go back and forth a few times, and this will converge on good estimates of latent variables as well as this hidden information. So basically, what fraction of the 2-2s are attributable to each of the possible cases. So does that make sense to everyone? Okay, so let me walk through one other example that I think may show some other advantages of EM and is motivated by similar kinds of biology. And that is, let's assume that we're looking at haplotypes here, but now I'm going to assume we've got a sequencing machine that does in fact give us the haplotypes, but it's noisy, so it makes some mistakes. And what I'm going to assume is that we run our sequencing machine, and sometimes, usually it will give us the right answer, but sometimes it gives us a mistake, sometimes it's just missing information. So it might be that we look at 3 variable sites in the genome, and we look over a bunch of people's genomes, and it tells us that we've got 100 copies of the genome 010, and it tells us we've got 1 copy of the haplotype here, so let me emphasize these are haplotypes, not genotypes, tells us we've got 1 copy of 01, I'll say asterisk here, or 01 star, and the star here means that the sequencing machine couldn't figure out the base here. It tells us there's some missing information, and unfortunately that's a very common thing you get in real data sets. And let's say it tells us that there are 100 copies of 110, and it tells us there is 1 copy of 100. Well, if we were looking at this data set, then we could probably guess what's going on here. We would probably say that 010 is a very common haplotype in this population, and this 01 star was a failure to read one of these. So 01 star was probably really a 010, and so we really had 101 010s. We could also say that 110 seems to be a very common haplotype. So if we see just one example of 100, probably this was a misread, and this is really a 110. So the real clean data would have been 101 copies of 010 and 101 copies of 110. Does that make sense to everyone? All right, so this is another example of a problem in which we might be interested in using expectation maximization. In particular, what I'm going to assume here is that we've got this noisy input. And what we're trying to do is to denoise the input. So we're trying to figure out that really what we have is 101 copies of 010 and 101 copies of 110. And this is another kind of problem in which expectation maximization tends to be very useful. So EM tends to be really good at these kinds of denoising problems where you're assuming you've got some noisy data and you're trying to figure out what the denoised data looks like. It's very widely used for problems of that form, and problems of that form come up quite a lot when you're working with experimental data of all kinds. So to turn this into a computational problem, what I'm going to do is pose the model we're trying to find, which will be just like we had before, frequencies of haplotypes. But here I'm going to assume that we now have 3 variable bases we're looking at, just to make it a little more interesting in this case. So we're going to have 8 possible haplotypes that we could observe here, and we're going to assume that our input is this noisy data. So counts of how many of these we think we've seen. So we think we've seen n000 copies of 000, and n001 copies of 001, but also n00 star copies of something where the machine told us is 0 in the first position, 0 in the second, but it couldn't read the third position, and so forth. So n010, and 011, and 01 star, etc. So we're now assuming we read haplotypes, but we get noisy readings of them. So does that make sense to everyone? All right, so if you want to come up with an EM algorithm for a problem like this, the first step in that is trying to come up with a model of the noise in your system. To try to come up with a probability model that tells you how likely you are to observe any particular observed value given the real ground truth value. And if you can do that, then you can come up with a likelihood function expressing the complete probability of your observed values given your assumed true values. So one thing we would need to do is pose a model of missing data. And a simple thing to assume is that there is some probability of failing to observe a value. In other words, the probability we observe a star, given we had a 1, we'll assume is the same as the probability observe star, given that we actually had a 0. We'll just call that mu. That will be some parameter. And then we could say that the probability you observe, let's say, 1 star 1, given that you really had 1 0 1, would be equal to the probability you observe a 1, given that you really had a 1, which is 1 minus mu, times the probability you failed to observe the 0, which is mu, times the probability you observe the third position, the 1, given that it was really 1, which is 1 minus mu. So that would give us a likelihood for a particular haplotype observation. That would be the same thing as probability observe 1 star 1, given that it was really 1 1 1. That would also be 1 minus mu, mu, 1 minus mu. So observe the first base, fail to observe the second, observe the third. Is everyone following me so far? We then need to extend that model to a model of erroneous data. A model of errors. And what we'll propose is that there is some probability that we flip a base. So in other words, probability we observe a 0, given that there is actually a 1 in a given position, the same as the probability we observe 1, given there is actually a 0. Those wouldn't necessarily be the same for a real sequencing machine, but let's just declare that they're both epsilon. And what we can then do is extend this model to say that, let's suppose the probability we observe 1 0 1, given that we really have 1 1 1, that would now be, in this extended model, the probability we observe the first position and don't observe it incorrectly, which would be 1 minus mu minus epsilon. So we didn't fail to observe it, and we didn't observe it erroneously. In the second position, we observed it erroneously with probability epsilon. In the third position, we observed it and observed it correctly, probability 1 minus mu minus epsilon. So does that make sense to everyone? All right, so if we can figure out the probability of observing a particular sequence given the real ground truth, then we can generalize that to the probability of observing the sequence at all. So let's say the probability of observing 1 star 1 by just summing over the possible ground truths that might have produced that. So one possibility is that we observe the first and third bases correctly. There are 2 haplotypes, 101 and 111, that would give us correct observations of these. So that's the frequency with which we would see those. And then we would make that correct observation of the first base with probability 1 minus mu minus epsilon, fail to observe the second with probability mu, and observe the third with 1 minus mu minus epsilon. We could similarly say that it's possible we misobserved the first position, so the real haplotype is 001 or 011, and then we would have probability of an error in the first position, fail to observe the second, but correctly observe the third. Or we could have made a mistake in the third position, so the real haplotype is 100 or 110, observe the first correctly with 1 minus mu minus epsilon, fail to observe the second, misobserve the third, or we might have misobserved both positions. So the real haplotype is either 000 or 010, and we assume we misobserved the first position, failed to observe the second, misobserved the third. So this then would be the likelihood of this observation. And if we were putting together the complete likelihood function for the problem, what we would need to do is take this observation, take this thing raised to the power n 1 star 1, so that's accounting for the likelihood of all 1 star 1 observations, and multiply that over all of our, in this case, well, it would be 3 to the 3, or 27 possible observations. So does that make sense to everyone? Okay, so let's then propose an EM algorithm to solve for that problem. So just as before, we need latent variables. So we'd like to find some variables that will make this problem as easy as possible to solve. So something we wish we knew about the system that would make it easy to solve the model inference problem. So what would be helpful to know? Well, the reason EM tends to be really good for these denoising problems is that there's usually a very obvious answer to what the latent variable should be. So the latent variable should be the denoised data. So if you're assuming you've got noisy data, you propose that your latent variables are the data with all the noise cleaned up, and then you come up with an EM algorithm that lets you try to figure out the frequencies from that data. Because if we had the denoised data, it would be very easy to find the haplotype frequencies. It's just counting. And as we'll see, you can, if you have the haplotype frequencies, you can get a good estimate of the denoised data, or at least the counts of the different sequences. So, for example, we would have an M step. And let's say that we're assuming that our latent variable is what I'll call this denoised data. So capital N000 is the true number of 000 haplotypes. Capital N001 is the true number of 001s. Capital N010, true number of 010s, and so forth. So we're going to have 2 to the third of these, so 8 possible true values, in comparison to the 3 to the third, or 27 possible noisy values, because the true values are never missing information. All right, so the M step is going to be where we figure out the frequency of ijk, or at least find the maximum likelihood estimate of that. So how would we express that in terms of the observed data and the latent variables? Well, to make it a little easier, let's just define capital N without a subscript to be the sum of our x values, or it could be the sum of the y values, let's say sum over xyz of n xyz. So n is our total number of observed haplotypes. Then the frequency of haplotype ijk is just nijk over capital N. If we had the denoise data, the frequency of any haplotype is just the number of observations of that haplotype divided by all the observations. So that's pretty straightforward. And just as before, we can observe that this is linear in the latent variables. So it's only depends on a single latent variable scaled by a constant. So again, all we really need are the expected values of the latent variables. And that part, unfortunately, is a little complicated in this problem, but the principle behind it is not so complex, just the formulas get messy. So we need an E step in which we are going to find our expected values of the latent variables, and that's going to look like the following. So if we take n000 as an example, what we're trying to do is figure out what is the expected number of true 000s given the models or belief about the frequency of each haplotype and given the observations, the actual counts. And basically what it comes down to is saying how much of each count is attributable to this haplotype. So we'll have some observed little n000 values, and some fraction of those will really have been correct 000s. And that fraction will be given by the frequency of the 000 haplotype times the probability of observing that correctly, which would be 1 minus mu minus epsilon cubed. So that's the probability. We actually had a 000. We observed the first base correctly, we observed the second base correctly, and we observed the third base correctly. And then we have to normalize that by all of the things that could contribute to the 000 observation. It could be a correct observation with exactly that same frequency we just put there, or it could have been that we had something that was really one base off, so F001 or F010 or F100, and we incorrectly observed one base, correctly observed the other two. Probability epsilon times 1 minus mu minus epsilon squared. Or it could be that we were missing a particular value. Or excuse me, no, we're not missing any values here. Could be that we were incorrectly observing two of these. So maybe it was really a 011 or a 101 or a 110, and we misobserved two of them with probability epsilon squared, 1 minus mu minus epsilon. Or it could be that we misobserved all three of them, so it was really an F111, and we observed all three bases incorrectly with probability epsilon cubed. So this thing is going to give us then the probability fraction of the observed 000s that were actually 000s in expectation. Does that make sense to everyone? It gets a little messier when we consider, let's say, a case like what fraction of 00 stars are really 000s, because then we have to consider that some fraction of 000s that we'll have will be observed as 00 stars, in particular 1 minus mu minus epsilon squared times mu is the fraction of these that would be observed as a 00 star, and then we would need to normalize that by all the ways you could generate a 00 star. So that's going to be, 000, F000 plus F001 times the probability of observing the first two bases correctly and failing to observe the third, plus the possibility that we might have one base wrong, so F001 or F101, or 1, 0, 0, or observe one base incorrectly, we observe one base correctly, and we fail to observe one base, and then we would have to keep going. So not going to bother writing all of this, but run through all the things that might have been observed as a 0, 0 star, and then repeat this for every possible observation. So as I say, it gets kind of complicated, but that pretty much gives us our algorithm. You've got your end step, you've got your E step, you come up with some initializations, maybe randomly attributing each of the observations, assuming there's some fraction of them attributable to each possible haplotype, and then you just repeatedly cycle through using your E step to get your latent variables, use your M step to improve your model, and a few rounds of that is likely to converge on a very accurate denoising of your data. Does that make sense to everyone? Okay, so I'm going to stop there. I will say that most previous years I went through an additional lecture on hidden Markov models, because those are a great example of a more complicated use of EM where you can't get away with that trick of using expectation. But usually every year, almost everyone tells me you've seen hidden Markov models somewhere else. I decided to try skipping that this year. Just by a show of hands, how many of you know what a hidden Markov model is? And okay, you'll probably see that if you're taking Dr. Duran's class. If you haven't seen it yet, I think you will be seeing that. Basically, there's a standard algorithm for learning the parameters of a hidden Markov model called the Down-Welch algorithm. It's a nice example of an EM algorithm. So I'm not going to do a lecture on it, but it's covered in the text. So, and I think I have some supplementary notes on it. So that's a good thing to read about if you want to see a more complex example of EM. So are there any last questions on anything before we break for the day? Okay, so we'll stop here. I do have some homeworks to hand out, so let me get those.